Okay, so let me start by joining everybody else in thanking the organizers. It's really a delight to be back here. Okay, it's still a delight to be back here. It's a place I've been coming to for many, many years, so it's always a wonderful, wonderful place to be. I'm very delighted to be here. So there hasn't been really much discussed in terms of numerical methods and numerics at this conference, and I'm going to be focused on this. So I'm going to be reporting numerical simulations and experiments, and I'm going to be focusing on our deceptively simple Hubbard model, which, with all of the progress that's gone on over the last decade or more or so, we really do have quite a good understanding of the myriad number of intertwined phases that are in this very, very simple model, with a lot of features or a lot of phases that have analogs in the cuprates and when properly generalized to other transition metal oxides and so. And so I don't have really any time to discuss many of the things that have been discussed here in this building over many years and many conferences. And so because I want to focus on the topic of this conference, which is about transport, in which we have much less exact results. And so I'm going to be talking about simulations that are done using a quantum Monte Carlo methods to try to investigate this in a bit more detail. And as we've heard from the wonderful set of talks, and in particular Erez's talk, I'm going to just sort of echo that. We know that this is a great diagnostic, the Wiedemann-Franz ratio, to sort of probe and test transport in systems which are both weakly and strongly interacting. And we know if there is a violation that this doesn't necessarily correspond to being a non-Fermi liquid, and the converse, which has been discussed, is if the quasiparticles are poorly defined, it doesn't necessarily mean that Wiedemann-Franz should be violated, and in fact, there are many cases in which it holds, as we've just heard. And so the message of my talk is going to be that even in this Hubbard model, from what we can simulate, and so it seems that this also seems to hold as well. So as usual, there are heroes involved in this, and I'll try to explain why I use that title. These are students, Wen Wang, Catherine Ding, and a newly minted Professor Edwin Wang. All three are here in the audience, and of course they did all the work. So, and in fact, they should probably be the ones who are giving this talk. So I'll discuss more in detail what they do as we go. But there are other heroes, because what we are doing is based out of this paper, which came out in 1981. And I'm very delighted that Doug is here, because this is really our Bible for quantum Monte Carlo, and it's used for lattice gauge theory today still to calculate quark masses, for example, and G-2 for the muon and so on, as well as for study of correlated systems. So really, we're really indebted to Doug and Bob Sugar and Dick Blankenbeckler for putting this together. But what you may not, well, you probably do know, but also at this time, these gentlemen were very busy and very connected to why we're sitting here, in that they were also the people that are involved, this gang of four, along with Jim Hartle and Ray Taylor, for starting the Institute of Theoretical Physics with a grant from the National Science Foundation and other things. So, and in fact, this came, I think this started around 1979, if I'm right, Doug, approximately, or so, right around when the time when this this paper came out, which is really a great example of different groupings of people and different research areas coming together, which is what an Institute of Theoretical Physics really is all about. So very indebted to these gentlemen. So let me just very briefly run through what that algorithm is all about. It's the algorithm we all use. We're starting off with trying to manage this gargantuan complexity, where if we have just a single orbital, and so we have 4n configurations of interacting fermions that scales exponentially with n. And what we want to do with the quantum Monte Carlo is we want to decouple the electrons by introducing an auxiliary Ising field, in which which can take up or down or plus or minus 1. And then we simulate these electrons moving in this auxiliary field in a space-time with d+1, where one of the directions is imaginary time, which we typically break up into time slices, which are controllable errors that we can manipulate. That's the Trotter error that's easy to control. So this is exact, and instead then what we do is sampling over all of these configurations stochastically using metropolis importance sampling. That reduces the complexity from exponential to polynomial, which means we can do much larger systems than we might do, say, from exact diagonalization. Of course, there's no free lunch, and the fermion sign comes in, and that restores back the exponential complexity for at least for many models, except in certain circumstances. So here's that issue that we have to face. This is the fermion sign plotted here versus this is electron filling. And these are various different cluster sizes, values of U and T prime that one investigates. And so this is inverse temperature beta here. So this is going from beta of a half, that's hot, down to beta of 5, which is about as cold as one gets, where the sign sort of tanks out at, this is on a log scale, on 10 to the minus 3. I just want to emphasize that there's nothing fundamentally bad about this. It's just an issue of how much you want to tolerate, how far down you want to go, because then you just need to sample more in order to get enough statistics to work with having a very small sign. And so unfortunately that goes exponentially. So in order to show you the data that I'm going to show you, you're looking at measurements which have been done by those 3 people I just indicated, which are tens of millions of measurements, so on the order of millions of CPU hours that you need in order to be able to get enough statistics to accurately work at the temperatures that I'm indicating. And so just to give you an idea of what's... Do you understand the minimum? Say again? Do you understand the origin of the minimum? Do I understand it? No, I don't understand it. I hope somebody does. That would be great. But yes. Yeah, I'm sorry, I only have U of 6 here. Of course, increasing U does bad things to the sign. So we don't want to, and we also don't want J to get too far down, so that would limit also our temperatures that we could access. We want to get, as I'll say, oh, I put it here. We want to get underneath the scale of the antiferromagnetic exchange, and we can do that with a reasonable value of U, which you can't take to be too small because then we lose all of the physics that's important to keep at half filling. Yeah, I mean, I'm happy to show anything offline about the numbers and so on. So beta 5, just taking some reasonable guess for what the hopping T is, about 1/4 volt or something like that. That means we're limited by getting down to temperatures roughly about 600 Kelvin. This is something we have to live with. Yet, as I said, we can get underneath the scale J. So we can ascertain what's the ultimate fate at T equals 0. That's better in the domain of DMRG. But we can at least calculate things that DMRG has a much more difficult job of calculating. Okay, so what we are evaluating are Kubo correlations, functions that we need for transport. And so what we evaluate is some operator expectation value in imaginary time. This is the thing which you evaluate with quantum Monte Carlo. This is the thing we want because these correlation functions are the things that give the electrical conductivity, the thermal conductivity, and the thermal power. These are the 3 things that I'm going to talk about in the talk. And the difficulty comes is because as you go down this list, you have a large number of fermion operators that you include here. And that means you have lots and lots of dynamic range that you have to make sure that you cover. And so this means that, again, not only is it you're fighting the fermion sign, but you're also fighting enough statistics in order to accurately determine these correlation functions, which get quite complicated because not only do we have just simple single particle currents, but we have energy currents and so on that we need to take into account. Okay, so what we do is, as I said, we evaluate this. This is what we want. So what we can do is what's called analytic continuation, and unfortunately there's no unique way of doing this, so this is another caveat of our approach. However, we've thrown everything we can at this to try to make sure that there's many checks and so on that one can do to at least have a reasonable good idea that our confidence level of determining these real frequency quantities can be quite good. And we can check that with other things which just are proxies which involve no analytic continuation by evaluating, for example, the current correlation function at imaginary time beta over 2, which in the limit t goes to 0 should go back to being the thing that we want. So here is, with those in mind, that's where we are, those are the caveats. So let me just get into the results. I'm not going to show you everything, so I'm just going to show you, for example, Fermi surfaces. So A of k omega equals 0. It's hard to see, but this is hole doped Fermi surfaces at the top. That's 5% doping off of half filling, 10%, 15%, where you can see the Fermi intensity brightest at the node and falling away as one goes to the antinode, and then as one continues to dope, the spectral intensity gets brighter and extends out further towards the zone boundary. And then this is electron doped 5%, 10%, 15%, where on the electron doped side, this line, you can't really see, but the antiferromagnetic zone boundary is kind of like a dissector of the spectral function, where you can see very clearly that as it cuts through, as the Fermi surface cuts through, you get a suppression of spectral weight. This is what was known since Peter Armitage's early data in photoemission. So there are many other things. Unfortunately, that's some other time. So let me continue and show the optical conductivity. So this is sigma of omega versus omega. This is half filling. Oh, sorry. The doping disappeared on this. So this is half filling. And what one can see, this is omega over t. So there's a peak, which would be the absorption edge, followed by a shoulder, which is set by the Hubbard U. And then as one goes hot to cold, one sees that the low energy intensity is going away as the gap opens up and you're in the antiferromagnetic insulating state. As one dopes, these are two different hole dopings, and that gap is closed, and then instead it reverses, where you see a very nice Drude peak show up, but yet that large energy continuum still stays there. And so what we can then look at is we can look at, for example, if you'd like, the width of this peak, or just take the DC value and plot that as a function of temperature. And so that is the resistivity. Unfortunately, the scale went away, but that's in units of h bar over e squared. This is over a very high temperature range, and you can see it's very linear, except at the insulator where it turns around and goes up. So this is not a surprise that it's linear at this at high temperature. In fact, that's something you can do analytically at high temperatures. But the thing that is really surprising is that there's really no apparent change of slope as one goes down, coming down from high temperatures. So if you blow that region up, here's the insulator, that's 5% doping, and then you see as they come down, it just with increased doping just sort of stays linear, following that same slope that's coming down from high temperatures. Yes?
Can you verify whether it's thermal or not, whether it's elastic scattering?
Right, so I would have to go and look at the self-energy and try to separate that out in terms of looking at Matsubara moments and these sort of things. And so we haven't really done that enough to say conclusively whether it's thermal or quantum that's giving rise to that. And that's one of the good things is we don't need to look at the self-energy to calculate these things or to investigate them. And of course, depending on whether you like 2 pi equal 1 or not, most of these curves are above the Matyaffe limit. Okay, so if you then take the, that's the resistivity just shown again on a larger scale, we can evaluate the compressibility. That doesn't involve analytic continuation. The fact that the inverse compressibility goes like 1 over T at large temperatures is easy. That's in fact derivable analytically. And then as it comes down in temperature, it's just kind of saturates and goes or converges to a constant. And so that means if we have an Einstein relation, what has to take over the temperature dependence as one goes down in temperature is really the diffusivity. So the inverse diffusivity is the one who takes over the linear and T temperature dependence. So even though the resistivity looks just like a single line, it's really a handoff between compressibility and, oh goodness, all right. So for thermal conductivity, we have to evaluate the energy currents along with the single particle currents. Let me just start with walking you through what happens at half filling. This is an older plot which just shows you that if you look at the magnetization, that up at high temperatures we have free electrons basically running around each side. Each of the end of 4 states are equally probable, so this is mz is a half. And then for different, as you go down in temperatures, local moments begin to form, and that's set by U. And then what's important is that this turns back over as the magnons start to appear and start to propagate. So if we think of the thermal conductivity then, which is shown down here along with the specific heat, then you could see exactly what you'd expect from having moments form, which is set by this big broad peak here in the specific heat. That's showing the thermal conductivity, which grows. And then we get a magnon peak down at low temperatures, which is when the magnons start setting in and becoming coherent, and the thermal conductivity develops a foot down at very low temperatures. So if we blow that region up, then you see here's the peak in the specific heat, and now while the arrows here was U over 4, now the arrows are denoted scale roughly about J, where you can get over the specific heat and see the peak, and then the thermal conductivity starts diverging as the magnons become long-lived. And so I don't know if this is helpful or not, but we can separate the operators that we look at in terms of 2 pieces, a particle current and an energy current that I can separate into a part which goes like the single particle hopping T, and then another part which is coming from U, from the potential energy piece. And then what we put that in to evaluate these correlators, and we could look at, say, a kinetic energy contribution to the thermal conductivity from the particle current, and this part here, and then the potential energy piece, which comes from this part. Of course, all of the things that we're evaluating have the Hubbard U in them. It's just this is a way of separating the operators to see how we can get a better understanding. And what you see is this is a specific heat and thermal conductivity, and these are the 2 pieces. The solid lines, the potential energy contribution, and the dotted ones are kinetic. So you see at high temperatures, everything is kinetic. It's half filling, free electrons are running around independent of what U is. And then as one comes down in temperatures, then the potential energy piece starts kicking in. And one sees that that becomes, in fact, dominant and gives the peak in the specific heat, but it fights the kinetic energy part. So summing them together is what gives the peak in the specific heat and gives the little foot down in the thermal conductivity. And so, again, then just blowing that up on the low temperature scale, you see the 2 contributions fight each other for the specific heat and as well for the thermal conductivity. And so then dividing out by the specific heat, then we could look at the thermal diffusivity, and it looks relatively constant at high temperatures, drops down as these magnons start to develop, and then eventually turns around and becomes divergent, and that divergence is just going to be cut off by the finite size of our cluster. So I have to move quickly because I want to show the thermal conductivity. So here is the electrical conductivity and the thermal conductivity divided by T. This is for the strange metal case. These are the different dopings. starting from half filling up to 30% whole doping. So you can see at half filling, these two are not are similar, but what's more striking is one gets into the strange metal phase that they look very similar to each other. And so if we take the ratio of them, then at high temperatures, you can see there's a very, very strong separation, a very strong doping dependence. Again, this changeover that I showed in half filling still works out here. But then as one gets down to temperatures roughly about J, these doping dependents start collapsing and they start forming on the same line, and that is pi squared over 3. So I can't tell you whether or not that hits that mark, but at least it's on its way and approaching from below, as what Eras was showing earlier. Again, we can, well, first we can look at, does it depend on the Fermi surface? Does it depend on the value of U? So we have plenty of Umklapp here, but what you see is that there is a strong dependence up at high temperature, but this collapse that one sees going down to low temperature doesn't seem to be very affected by the hopping and or the Fermi surface or the value of U that one uses. Once again, you can separate out the ratio, the Wiedemann-Franz ratio, into these two contributions, a kinetic energy part and a potential energy part. And if you look at them separately, this is the kinetic energy part, it overshoots the Wiedemann-Franz value, and the potential energy part actually compensates. As one changes the doping, this is overshooting, for example, 5%, and this is undershooting, and that's what, when you put them together, gives something that gives the apparent Wiedemann-Franz ratio. And so, do I have 30 seconds? Yes. Okay. Just to discuss the thermal power, because what's good about the thermal power is that there's a ratio of correlation functions. So all units drop out, all parameters of the Hubbard model drop out, and one is left with just constants that give you a way to really kind of quantitatively get a handle on the value of the thermal power. So this is the Cooper thermal power that's from many years ago, which has a kind of ubiquitous. There's many different samples here. Decreases or increases with decreasing temperature, and then it has a sign change at around 18% or so. And it's a bad way of plotting this. This is a log scale, so it goes exponentially with temperature here, and goes like this is linear, so it goes like a power law for different hole concentration. And importantly, this is at 290 Kelvin. So this is closer to the regime that we're looking at. So we can look at, for example, the comparison between the Kelvin expression, which has been indicated as a proxy for the thermal power. They're both related to each other, the Kubo expression and the Kelvin formula, by limits. And by looking at both of them, indeed, you find that they are, it's thermal power calculated with Kubo, thermal power calculated from the Kelvin formula, which is just thermodynamic susceptibilities. And you can see that they're about the same, that they rise up steadily with decreasing temperature, get stronger as one goes to lower doping. It really doesn't depend very much on the values of U or the shape of the Fermi surface. And this crossing, where it hits 0, is not set by the Van Hove or set anything according to when the Fermi surface changes its shape. It's really set by this isospastic point, which is in n versus mu. In that sense, it's somewhat independent, or not as dependent on things like U and the hopping. So, and then if we overlay the experimental values for these 6 samples, along with the calculation for different values of U or different values of T prime, and again, all we have to do is translate our hopping in terms of a temperature. There's nothing else that we do. Not only does this give kind of a good qualitative agreement with the doping dependence, but also quantitatively, it's in pretty good shape. So I think I've taken all of my time. I'll leave my summary up there, and thank you very much.
Tom, in your list of other things that you said you're not going to talk about, I don't know if I saw correct. Do you have something to say also about the Hall angle?
Yes, I do.
Do you want to?
Can I show it, or is okay?
He did not pay me to ask that.
No, I didn't pay him.
But he will.
I will pay him later. Yes. Okay. Oh, yeah. See, you didn't want to ask that. 1 second. Okay, so just very, very quickly, there are different ways to evaluate the Hall response, either in a way of looking at a 3-current correlator or a way from Asa-Auerbach, or actually just including the magnetic field. So we've used all three. So this is the Hall coefficient as a function of temperature from and 4 different values of U. Of course, at half there's no T prime, so it's particle symmetric. So there's nothing here, of course. But as one dopes off, you can see that there's a very strong temperature dependence that, and in fact, can even have several different crossings. And so that is maybe what you might have expected, where you can go from Hall to electron and so on. But the thing that was surprising is that that number and the temperature dependence really just follows from looking at the enclosed area of the Fermi surface. So even though it's a very strongly interacting problem, the topology of the Fermi surface really does tell you something about the Hall. All temperatures. All temperatures. Yeah, because the Fermi surface changes with temperature. Yeah.
You probably said it, but in case I missed it, if you take 1/tau from the resistivity in the usual way, Planckian, sub-Planckian, super-Planckian, what's the coefficient alpha?
Actually, we see that it goes linear in T. I forget what the actual number is in terms of a bound. Edwin, do you remember? Order 1. It's order 1. Yeah.
If it's elastic, it doesn't matter. There's no Planckian.
If it's elastic, but we don't know.
The slope doesn't change from very high temperature.
Yeah.
And at high temperature is definitely elastic.
Yeah.
And then if you continue your linear temperature dependence, it seems to intersect the vertical axis at a finite value. So there is no disorder, right?
There's no disorder.
In your simulations.
Yes.
Is it an artifact of sign problem?
No, it's an artifact of analytic continuation. Because unfortunately, once that Drude peak gets to be smaller than temperature, kBT or so, then you have the most terrible thing that you have to do analytic continuation on, which is a sharp peak and a broad continuum and another hump that sits out there. That's really bad. Okay, I'll be corrected. Go ahead.
No, I'm going to start arguing. It's also called, around the same time our paper was published, there were also some code atom experiments where they try to study the same problem, and then they're doing this in real time, no analytic continuation. And if you look at their data, there also seems to be a bit of an offset in the extrapolation to 0 temperature. So it's a combination. Of course, the analytic continuation doesn't help there. From the code atom experiments, it seems that there's really something causing this offset.
Hi, here. So I was wondering about, because you showed beautiful data agreement with theory for the thermal power. So I was wondering for the slope of the T-linear resistivity. So you could go down to around 600 Kelvin. So there are some cuprates like BISCO 2201 or YBCO where the T-linearity actually extends to around the same temperature range. So I was wondering if you compare the slopes to see if they quantitatively actually are close to each other.
Yeah, I think one could. I just want to, I'm not saying the Hubbard model is the cuprates. I just want to make that clear. We do the best job we can based on the model, and it is remarkable how many things actually are reflecting what's going on in the cuprates. When it comes to being quantitative and really making, direct contact with experiments, I'm on much shakier ground because, we're abstracting, in terms of just nearest neighbor hopping and not many hoppings. And you know, and don't know exactly what the value of U should be and these sort of things. So yes, we can make contact, but I'd prefer to make contact with things which don't depend as much on the parameters that we put in.
Okay, so let's think.